Finally, we will talk about random walk on the graph. So let G be a finite, undirected, and connected graph. Based on this undirected graph G, we will make some changes so that we are going to make this directed. So what we are going to do here is that we are going to replace each of the edge UV of G into two directed edges UV and VU. And then a random walk on G is a Markov chain such that the transition graph, the directed graph representation is this dg. And moreover, for each edge uv, the transition probability is 1 divided by degree of u. So let's take a look of an example first. So suppose that this is the input graph G that we have. So it has 4 vertices. And then these are the edges and directed edges there. So in order to talk about the random walk, first of all, we change G into a directed graph so that each of these directed edge is replaced by a double arrow edge. So one going from forward and one going backward. Is that okay? And after that, we add the transition probability for the edges. So basically, for each node, it will have the same probability for each outgoing edge. So because 0 here has 2 edges connected to it, so half of the chance it goes to 1 and half of the chance that it goes to 3. And for instance, this state 2 has only 1 edge joining it. So with all the probabilities, the edge from state 2 to state 3 will have probability 1. So basically, this means that this wants to simulate the following behavior. Suppose that there is some person walking along the graph G. At each time, when we are staying at a certain state, let's say state 3 here, then it chooses with equal probability what is the next edge that he will traverse. So this will give us the corresponding Markov chain. Now, since the graph G is assumed to be connected, so the Markov chain, the corresponding Markov chain is irreducible. So it is easily checked. Every state can reach every other state. Now, the second part here is if someone tells you that this G is not bipartite, then the corresponding chain will be aperiodic. Now, the reason is that whenever the original graph is not bipartite, for instance, this is not a bipartite graph. Whenever a graph is not bipartite, then there must always be some odd length cycle like this one. This is an odd length cycle here, length 3. So in that case, we will have an odd length cycle so that we can see that for every state like this one, it can always go back to itself by visiting a neighbor and back to itself. Yeah, because the graph is connected, it must have a neighbor, so it can go to a neighbor and then back to itself. So it's always possible to go back to itself in 2 steps. And also, it is always possible to go back to itself in odd number of steps. The reason is that we find a way to go to the odd length cycle, traverse the odd length cycle 1 round, and then go back to itself using the same way as it goes to the odd length cycle. So we will see that the total length will be going to the odd length cycle, traversing the odd length cycle, and going back. Going to the cycle and going back has the same length, so this is an even number. And together with the length of the odd length cycle, it will be odd in total. So in other words, every state can go back to itself in an odd number of states. Now because of this, every state can go back in 2 steps or go back to itself in odd steps. So in that case, the GCD is going to be 1. So every state will not be periodic. So the chain itself is aperiodic. Okay? So from now on, we assume that G is connected and G is not bipartite. So the corresponding chain is irreducible and also aperiodic. And we use this new notation, h of uv. H of uv represents the expected number of steps to move from state u to state v in this chain. Now we have the first theorem. In the random walk on G with this property, then for any vertex v, hvv is equal to 1 over pi v. So sorry for the mistake, this is going to be v. And then it is equal to 2 times the number of edges divided by the degree of v. So first of all, this one is already implied by the previous theorem. And then in order to show this theorem is correct, it is sufficient to show that the latter part is correct. So in other words, we want to show that for the distribution pi equals to this one, where pi j equals to degree of v divided, there's another mistake here. So this is pi v is equal to the degree of v divided by 2 times the number of edges. Then this represents a stationary distribution. So, okay, so let's see. Okay. Now, to show that this is a stationary distribution, what we can do here is that suppose at time t, the distribution at time t is exactly the same as the pi that we have defined here, with pi equals to this kind of value. Okay. Now at time t plus 1, then let us observe that what is the probability that we are going to be staying at state v. Okay. So at time t plus 1, the chance that we are going to be at state v will be equal to what? So if I want to go to, so example, okay. So for instance, let's take a look at this example. Suppose that we have already arrived at the hypothetical stationary distribution. So at next time that we go to here, it must be equal to, we look at all the incoming arrows, right? So the incoming arrows will be from different states. Let's say state U, state W, state Z, something like this. So it will be equal to, the chance that we go to here will be the chance that we are going to be in this state multiplied by this transition probability plus the chance that we are in this state multiplied by this transition probability plus the chance that we are at this state multiplied by the transition probability. So in general, so this is the algebra formula. So we are going to sum up every u that pi u t is the transition probability, is the probability that we are going to be at state u multiplied by the chance that u can move to v in one step. So this is the same as if we are saying that we only need to consider those u that is a neighbor of v in the original graph. So when u is a neighbor of v in the original graph, the chance that we are going to move from u to v in one step is exactly the same as 1 over degree of u. And the corresponding probability that we are at state u at this moment before moving is the degree of u divided by 2e. So this is what we assume that we are at time t, we have this probability distribution. So if you multiply this term with this term, then we will see that the degree of u is cancelled. So it is 1 over 2e. And how many things that we are adding? The things that we are adding depends on the number of incoming arrows. And the number of incoming arrows to the vertex v is the same as degree of v in the original graph. So this is the degree of v here multiplied by 1 over 2e. So it is like this one. And this is the same as pi of v at time t. So what does that mean? Pi of v at time t plus 1 is equal to pi of v at time t. So this is going to be true for any vertex v. So what does that mean? It means that whenever we have arrived at the distribution as we stated here, then it will stay forever. So this is a stationary distribution. Now, because the graph that we have assumed to have is irreducible. I mean, the original graph is connected and not bipartite. So the corresponding Markov chain is irreducible and aperiodic. So in that case, this is the unique, the one and the only one stationary distribution. Okay, that handles the case where we are talking about the expected step to move from V back to itself. But here, we extend our result a little bit further. So let's consider any edge UV in G. So we can measure the expected number of steps to move from U to V in this Markov chain to be upper bounded by 2 times E. Okay, actually the proof of this one, so although they are linked by an directly in G, it doesn't mean that it is easy for one to go to the other one. But because U could have many different arrows going out, so it may not choose V as the next destination. So, but still, we can have an upper bound for the expected number of steps to go from U to V. So this is actually very simple. So we make use of the previous result, HVV, okay, that we have computed, okay, can be expressed as the summation of, so how do you compute HVV? Okay, so we are going to use the conditional expectation formula. So we need to consider all the neighbors of V only, because if we start from V, okay, in one step, we can only go to one of its neighbor in the original graph. So the expected value HVV can be expressed as there will be one step to move to a neighbor, let's say U, and then after that, if we are at state U, it takes HUV steps to go back to V. So in order to go from V to V, it takes one step to move out to one of the neighbor, and then HUV to go back to itself, the U from U to V. And the chance for this happening is 1 over degree of V. It is because each of the neighbor of V has the same chance to be moved from the current state V. So HVV can be expressed as this one. And together with the previous result, so this is the previous result, HVV is equal to 2E divided by degree of V. So we can plug in 2E divided by degree of V here is equal to the summation of this one. So degree of V and degree of V here can be cancelled, so we get 2E is equal to the summation of all this. And if we sum everything up, it is equal to 2E. And if we look at a particular term here, it has to be less than 2E. So in other words, we have proven the lemma. Okay, next, based on the random walk on the graph, we can talk about cover time. So what is meant by cover time? So for a graph G, we let this notation cover of V to be the expected number of steps to visit all the nodes of G by random walk. And this little v specifies that our starting point is V. Okay, so cover of V is, we start from V. What is the expected number of steps that we can travel around so that all the nodes of G will be visited? And we defined cover of G to be the worst case of all the possible cover. Okay, so the maximum of all the cover of V for every V. So we have, so in other words, okay, so if I know the value of cover of G, then I can claim that no matter which node that we start at, the expected number of steps that we need to visit or to cover all the nodes in G must be less than or equal to the cover of G. Okay, so we can have a claim like this. And here we want to show that cover of G is less than 4 times V times E. Okay, so how do we show the result? What we are going to do here is, let us consider traversing the graph G according to a special order. So here I mean logically. So let me define what is meant by logically. Okay. So let's say there is an order row that we start from V0 and then logically we go to V1 and logically we go to V2 and so on and so forth up to the end. Let's call it VZ. And in this traversal, all the nodes will be visited at least once. By means of logical, so it doesn't mean that V0 and V1 there is an edge connecting to it. So what we want to do here is that we start from V0 and we walk along until we go to V1. And even though we have traversed some of the nodes in between, we don't count them as visited, okay? And then starting from V1, we logically traverse and go to V2, so that from V1, we walk, and then until we hit V2, and so on and so forth. Once we traverse in this order, then this is the traversal that we are specified by this row here. So here, this is what I was just mentioning. So in case of random walk, when we traverse from Vj to Vj plus 1, then we may visit other nodes along the way. So it doesn't matter V1 and V2 are connected or not by an edge. It doesn't matter whether each adjacent two nodes are connected by an edge or not. Okay. Now, according to this row, then we will see that the cover time, if we start at V0, will be less than or equal to the expected number of steps to traverse by row. It is because when we traverse by this row, this is only logical. So before we end here, we may have already visited all the nodes. So in that case, we will stop when we are talking about cover. But for row, we have to stop until we visit this VZ logically until the end. So in other words, the number of steps that we are using by this row is always more than the corresponding number of steps in this traversal that we try to cover the graph. So the expected value, if we start from V0 to cover the graph, in that case has to be smaller than or equal to the expected value of this number of steps. So we haven't specified row. We just mentioned that whenever row has this property, we have this to be correct. And now to help our analysis, let us fix row to be an Euler tool of a spanning tree of G, where row will consist of 2 times V minus 2 edges of G. So what is meant by spanning tree of a graph, and then what is meant by Euler tool? So recall that the graph G is connected. So the graph G is connected, then we can draw some spanning tree for it. Any spanning tree will work. Now once we have a spanning tree, then we can talk about an Euler tool. So Euler tool starts from any node we traverse along the way, like this one, and then we go back. So this is the trace of the Euler tool. So if you look at this one, so this means that we start from this node, like this one, we go to this node. And then from this node, we go to this node. From this node, we go to this node. From this node, we go back. From this node, we go back. From this node, we go forward, go back, go forward, go back, go forward, go back, and go forward. And then we end it at the place where we started. So in particular, each edge has to be used exactly 2 times. One is going forward and one is going backward. So because the spanning tree of graph has V minus 1 edges, so the total number of edges here is equal to 2 times that value, so it is 2V minus 2. So this is the Euler tool of G. And then we fix row to be any, just any Euler tool of the spanning tree. So once we have fixed it, then the expected number of steps to traverse by row, this time, because row is always using an edge each time. So let's say this is U, this is V, so this is going to be the expected number of steps to move from U to V, so it is HUV. Is that okay? So we have proven that HUV is less than 2e. So this is less than 2e in the expected sense, less than 2e in the expected sense, less than 2e in the expected sense. So in other words, it is going to be less than 4VE in the expected sense. So cover of V0 is less than 4 times V times E. And notice that the right hand side is independent of V0. So we can repeat this argument for any vertex V in the graph and claim that cover of V is less than 4VE. Now because cover of V is less than 4VE for every vertex, then the cover of G, the worst case, is also less than 4VE. So this is the end of the proof.